So, you've just heard about AstroCat, ground control, a mouse, and a satellite. Let's think about our problem. So we know that AstroCat is floating around in space, and we would like to know where AstroCat is. However, at ground control, they can only look at AstroCat through various instruments. Fancy telescopes, radar, LiDAR, it's all going to be measurements. Now, AstroCat is at some true position in space. We'll call it again S, the state of the world. And AstroCat likes to be near the astromouse. Of course, there are satellites in space, and while we still don't know where AstroCat is exactly, AstroCat should not hit one of the satellites. So, our problem is, ground control would like to know where AstroCat is, and they'd like to know exactly where AstroCat is. What is the true state, S, of AstroCat's position? Of course, they don't have access to that, they just have a bunch of interesting and noisy measurements. So here we're going to represent that as a Gaussian distribution. The center of that Gaussian distribution, or its mean, will be what we think of as the most likely state where AstroCat is. But of course, there's some variance, some spread, and so we don't know exactly. Of course, we can use Bayes' rule and our measurements to try to come up with a better estimate of where AstroCat is. In this case, imagine that we had some prior knowledge of where AstroCat likes to hang out. That's the red curve. We get some new information, the likelihood based on a measurement, that's the blue Gaussian curve, and we will end up with a posterior distribution. That's the black Gaussian curve. And you're going to work through all of this in the next tutorial. Now, of course, we still need to decide where AstroCat is and where he might want to go, and to do that we need to think about, say, the loss if he hits the satellite, or the gain if he's near astromouse. And so we can think of this as a utility function. With the utility function, we can then, now integrating, calculate the expected utility based on a choice of where we think AstroCat is or could go. That's the utility given the now continuous S, the true state where AstroCat is, and a continuous point A, which is where we're going to estimate or decide to move AstroCat. And then of course we have to multiply this by the probability of AstroCat being there. So, where is AstroCat? Where should ground control AstroCat's jetpack to go? We need prior knowledge about AstroCat's location, measurements of AstroCat's location, utility of being at different points in space, and we will only worry about the position along the orbit of AstroCat, so it's a single continuous dimension. Let's think first about continuous probabilities, likelihood, and utility. This is just an extension of everything you did in the binary fishing case in tutorial 1. So, when we multiply continuous functions, any continuous function, it's just point-by-point multiplication. In this case, we need to remember we're not multiplying the random variables that underlie a distribution. So, multiplying two Gaussians together is not the same as multiplying the two random variables that have a Gaussian distribution. We often write the continuous function, f of x, equals the normal distribution, that's written with an n, where our parameters mu and sigma tell us about the shape of that normal distribution for a Gaussian PDF function. And n, with just mu and sigma, is a probability distribution. It's not a function. So this is just a notational thing, but you have to remember you're not multiplying the underlying Gaussian variables. We're going to use the Hadamard product to represent the multiplication. That is to say, you're basically doing pointwise multiplication, and this can be extended to matrices if you have multidimensional Gaussians. Statisticians may assume when you show a PDF multiplied by a PDF that it's a bivariate distribution. Now, we can think of any Gaussian as representing a true value, and uncertainty around that true value. In this case, that means they have different amounts of information based on how much uncertainty they have. The information in a Gaussian is inversely proportional to its variance. So, here on the left we have a Gaussian with a wide variance, and its information is therefore smaller. The Gaussian on the right has a narrow variance, its information is larger. Importantly, when we want to think about the relative information between two probability distributions, or at least in these Gaussian cases, we want to think about the relative uncertainty. So take the two on the left and the two on the right. Now, they're both wider on the right, so there's less information. But if we ask how much information is between them, what's the relative information, then in fact we're going to think of it as the ratio of these two variances. We're not going to think of it as their absolute information. And this means that when we bring new information in and we compare some old estimate that might be a Gaussian with some new information that might be a Gaussian, we're going to want to think about the relative information involved. Now, Gaussians are a little more special than we've already let on. Not only are they central because of the central limit theorem, the sum of two Gaussian random variables is also a Gaussian. Now that's adding the actual random variables. The product of two Gaussian probability distribution functions is a weighted sum of the Gaussians. And in fact, you're going to see you can put both of these properties together in the Kalman filter. But the weighting is also related to their information. So, what happens when we combine two Gaussians by multiplication? We get a third Gaussian. And the means are going to contribute information. They're going to contribute to that mean by a weighting that is proportional to their information. So here, the first Gaussian with mu1 is going to be weighted proportional to its variance over the total variance. And the other Gaussian is going to be done exactly the same way. And if you'd like, you can demonstrate this for yourself in part of the bonus tutorial. The other thing to remember is that information adds. So the variance in the final Gaussian is just going to be the variances in the other Gaussians. But here, because we're thinking of information, it's the inverse, 1 over the variance, that's going to add. Okay, cut and redo that. So, when we combine two Gaussians by multiplication, we get a new Gaussian, which is a weighting of the prior Gaussians. And the interesting thing is that the weighting is based on the amount of information in the Gaussians. So, their means contribute to the new Gaussian mean proportional to their information. Here, we see that A, the weighting for mu1, is related to the amount of information, that is the inverse of its variance, over the sum of the information. And the information is going to add. So the inverse of the variance for the new Gaussian is going to be the sum of the information from the original Gaussians. And if you'd like, you can demonstrate this for yourself in the bonus tutorial. Now, what if we wanted to represent a probability that has more than one location where there's something we call probability mass? In this case, there are two modes, two areas where there is a large amount of probability. One easy way for us to do this is by using a mixture model. A mixture model is one where we take a simple random variable, a discrete categorical random variable. Think of it as rolling a die, or in this case, flipping a coin. And each time we do that, we then draw a probability from one of two distributions that are useful. In this case, our favorite distribution, the Gaussian. So here you can think of it, I flip a coin, I either draw from Gaussian 1 or Gaussian 2. but they become a new continuous probability distribution. And so here we can define a mixture of Gaussians, and the mixture of Gaussians is simply a weighting for Gaussian 1 plus 1 minus the weighting for Gaussian 2. Each Gaussian, of course, will have its own center or mean and its own variance. Now, when we want to use utility to help us estimate some point that will be good in a distribution, we need to define what good is. And one way of defining this is to use something that we call a loss function. A loss function is a special type of utility function where we're really only interested in the difference between the true state of the world and our guess or our estimate. Let's look at a couple of these and see why they're interesting and important. So, you're probably familiar with squared error. It's used in basic linear regression. We often use it in machine learning. It has the nice property that it is a continuous differentiable function. And the mean squared error function is simply our estimate. In this case, we're calling it A minus the actual true state, S, squared. And importantly, this loss function also tells us the mean of the distribution. Let's consider another loss function, absolute error, simply the absolute value of the difference between our guess and the true state. Again, for probability distribution, this absolute error loss function has the property of returning to us the median. And then finally, we can take a little bit bizarre but very useful loss function, the 0,1 error. This one is just 1 if A is equal to S, and it's 0 otherwise. And this will return the mode of a probability distribution. And we're going to look through all of these in the next exercises.